Hello, student. We are going to work on a new example on the conjugate beam method. This example, we are going to analyze the simply supported steel beam and is subjected to loading, and this one have a special loading which is the uniformly distributed load. If you may notice many examples that's in the textbook or in the examination, the oral examination, they only consider the point load for the conjugate beam method. For the uniform load, you may use the unit load method to analyze it. But for this one, I like to show you as a guideline that you may see. We also use the conjugate beam to solve the problem of uniformly distributed load, but it's involved to determine the resultant force by the integration, and also you need to determine the centroid of the area, because for the point load we have the triangular area, but for the uniformly distributed load you're going to have the curved area. So that's going to involve some mathematics, and I hope you guys as engineer can solve it easily. Okay, so the loading of this problem is a special one, and the beam is simple. It have the constant EI or constant fractional stiffness along the length of the beam. We also have the problem with the different fractional stiffness along the length of the beam. That's I also present in the PowerPoint already. And the beam is steel, so E is 200 gigapascal, and the I is going to be 60 times 10 power 6 millimeter power 4, and you may notice most of the time we use the meter, so you got to convert the I from millimeter power 4 to the one that has meter power 4. So usually you know that 1000 millimeter is equal to 1 meter. If you power 4 it, that means you got to power 4 this also. So it's going to be what? It's going to be 10 power 12 millimeter power 4. So 1 meter power 4 is equal to 10 power 12 millimeter power 4. So for this one, you got to change it to 60, and then 10 power 6 divided 10 power 12, and this is going to be meter power 4. So that means what you're going to have is going to be what? It's a 60 times 10 minus 6 millimeter power 4. That going to be the conversion of the unit. Okay, and you guys can do so. I think I know that. And then they ask us to determine what? Use the conjugate beam method to determine the slope at A and determine the deflection at C, and also the maximum deflection of the beam. This beam is not symmetrical beam. So you may see most of the load are in the AC segment, see, and that means the slope at A gonna be larger than the slope at B for sure, because most of the force are here. And then you can sketch the deflection of the beam, but this time the maximum deflection won't occur at the midspan of the beam. Okay, for sure, because the beam is unsymmetry. So if you divide the beam by half, okay, what you have is the deflection what occur there, but the deflection will occur, okay, between point C and the midspan. So the diffraction supposed to be go here, and then it's going to have the maximum around here, and then it's going to return back like this. Okay, so somewhere here should have the maximum diffraction, and the point of maximum diffraction have some special thing, as you may know when we consider the equation. The maximum and the minimum of the equation occur when what? Occur when the slope equal to 0. So I think it's supposed to be Vmax allowed here. Okay, and then they ask us to determine the diffraction at C. So that means you are going to determine the diffraction about this point. But this point is very close to. Okay, and they also ask us to determine the slope at A. So this is going to be the slope at A. This is going to be zeta sub A. And also you're going to determine this one for what? For the slope at B. This is the slope at B. Okay, that's all the requirement that they asked us to find. This is for the slope, and this is for the deflection. And the conjugate beam, the slope is going to be what? The shear force. Okay, and the deflection is going to be the moment on the conjugate beam. And then this is going to be the elastic curve, but we are going to refine, make it more accurate. Okay, after we know the value of theta A, theta B, V sub C, and Vmax. Okay, next, what is going to be the analysis procedure of this beam? And we know that for the conjugate beam, we got to what? We got to draw the shear diagram, we got to draw the moment diagram, and then we got to convert the real beam above here to be the conjugate beam. Okay, that is our duty. And by converting the conjugate beam, you also use the moment diagram to convert into the elastic weight also. That is the M over EI. So the procedure, first one, we will analyze the beam to get the moment diagram. And then we draw the conjugate beam for the second. And the third, we analyze the conjugate beam to get the shear on conjugate beam at the slope on the real beam, to get the bending moment on the conjugate beam as the deflection on the real beam. Okay, that is according to the conjugate beam method. Okay, first let us start by analyze the beam. First, analyze the beam to find V diagram and M diagram. Okay, and doing this, we got to start by setting up the reference XY axis. And since the beam is 5 meters, let me scale it up by using 1 meter per 1 centimeter. So my beam gonna be 5 centimeter long. Okay, over here, and then 2 meter is here, and then this portion subjected to uniformly distributed load of 5 kilonewton per meter. So this is going to be 5 kilonewton per meter, and you also has the 10 kilonewton here at the point C. So at the A, you're going to have what? The pin, right? So the A going to have the A sub Y. Okay, and also the A sub X and the B sub Y over here, B sub Y. And then we will use the equation of equilibrium to determine the unknown reaction. Okay, this is 2 meter, this is 3 meter. Okay, set a summation of x sub x equal to 0 first, and then you put this as positive. You may have the a sub x, which is here, is going to be 0. So a sub x is 0 because we have no horizontal force. And then we may take the moment to some point, just summation of moment. Let's say at the A equal to 0. And this is looking for what? Looking for b sub y. B sub y going to rotate like this. So the rotation of b sub y is positive. And then what we have is b sub y gonna times 5. So it's 5. And then b sub y. And the 10 gonna be in opposite direction. So that is going to be equal to 10 and then times this. This is in opposite direction times this times 2. And then you have what? You have the repulsion force here. And this is going to be the total area of the uniformly distributed load. That is going to be 10, right? 5 times 2 is 10 kilonewton, which is 1 meter from point A. So you got to plus 10. Okay, but this 10 gonna time 1 meter. So you got 20 and plus 10, that is 30. So your b sub y gonna be like 30 divided by 5, and it's going to be 6, right? There is 6 kilonewton. 6 kilonewton for the b sub y. And next, last one, we can determine what? We can determine the a sub y. So we do the summation of f sub y equal to 0. This time is up, it's positive. So our a sub y gonna plus 6. And then it's gonna equal to, that's up. That is downward. Okay, and then you gonna pass another one. 5 times 2 is also 10. So by doing this, a sub y gonna be 20 minus 6 is going to be 14. Okay, kilonewton. And then you got the 14 kilonewton here. And by obtaining this, we come into our beam, and now our beam has the b sub y here of 6 kilonewton. So this is going to be 6 kilonewton, and this is going to be 14 kilonewton. And now we are ready to what? To draw the shear diagram and moment diagram. And let's see, for the shear diagram is here. We got to set this one x meter. This is 0. This is 2. This is 5. And along here is going to be what? V in kilonewton. Okay. And then what we have to draw the shear diagram, we move from the left to the right. And what we have for that is the what? Is we have 5 relationship to draw the shear diagram, right? Let me review it a little bit. What we have is what? dv by dx is what? The first one, dv by dx is equal to minus w. Okay. And then the second, v sub b minus v sub a equal to minus of the area. Area of what? Area of w. Okay. Between a and b. Okay, this is the area. And the third one, what we have is we have upward force. Delta v is plus. If we have downward force, delta v is negative. So we have about these 3 conditions. So what we should do? We move to the A. And we found the 14. That means what? we move to the A, we found the 14, we found upward force. That means delta V is upward. So if you like, you may put this one, okay, 14 millimeter. So you use 1 millimeter per 1 kilonewton. Okay, yes, 1 millimeter per 1 kilonewton. So this is 14. That is plus 14 kilonewton. That's the first one. And then you move inside it. When you move inside it, you found the distributed force. So this one is applied, you found this. So the slope, the dV by dx is going to be minus 5. So this one going to be minus 5. And minus 5 all the way until you arrive at over here, C. So you come to here. V sub C minus this one, minus V sub A, minus 14. V sub C is here, minus 14 here is going to be equal to minus of the area of W between A and C. So it's going to be minus 5 times 2. Okay, by doing this, you will get V sub C equal to minus 10 plus 14. And then that's going to be 14 kilonewton. So this is going to be 14 kilonewton. Oh, sorry, 4 kilonewton, not 14. 4 kilonewton, only 4 kilonewton. Because it's 14 minus 10, that's 4 kilonewton. So you got this for 4 kilonewton. You got this for 4 kilonewton, the 4 millimeter. Okay, that is going to be plus 4 kilonewton. The graph going to be something like this. Okay, and you may indicate the slope. Indicate the slope like this. And now you arrive at C, and the C has 10 kilonewton. So it's downward. It's going to be downward. Delta V going to be negative. So it's going to take this part down 10 kilonewton. So this is 10 millimeter. Okay, that is going to be plus 4 minus 10. That is going to be minus 6 kilonewton. And then you move past the C and is no distributed load. So the dV by dx is going to be what? No W. So W is 0. So this is 0. So it's 0. And then you got this of minus 6 kilonewton. And then it's up like this. Okay, this is the shear diagram of this beam. And we don't use shear diagram. We're going to draw another moment diagram because the moment diagram going to be the basis for our elastic width. Okay, we have this one for x meter again. This is going to be 5, and this is 2, this is 0, and then we have this one as the moment of m kilonewton meter. Okay, they provide this area to us, and what we have is dm by dx equal to v. The slope of the moment diagram is going to be equal to shear. Okay, and we also have m sub b minus m sub a, and then it's equal to area, not negative, area of v diagram between a and b. That is going to be the second case. And the third one, if you have this counterclockwise moment, delta m is going to be negative. If you have this clockwise moment, delta m is going to be positive. But since we have no m at all, so this is going to be 0 kilonewton meter. and this one also 0 kilonewton meter. If you have the value when it has the external moment and it has no external moment, so A and B has moment equal to 0. Everybody know that, right? Okay, by using this. And then what? And then you move here. You get what? You get this one. That means your slope here. So it's going to be really upward. So dm by dx equal to 14 positive. And then the slope reduce, and then it's going to be dm by dx equal to 4 on the left. Okay, on the left by using this. And what is the value of m here? We don't know. So what we have is m sub c. M sub c is here. We don't know yet. Minus 0 minus this. And it's going to be what? It's going to be equal to this area. It's going to be equal to this area. Okay, we know that it's going to be equal to this area. What's this area? This area of what? 1/2 of what? Of 14 plus 4. 14 plus 4 and time 2. That's going to be m sub c. M sub c going to equal to 14 plus 4. That's going to be 18 kilonewton meter. Okay, so 18. Let's say we're going to have 2 kilonewton meter for 1 millimeter. 18 is 9 millimeter. So we have this one for 9 millimeter. And this is going to be 18. Okay, and you have slope here also. Slope here is going to be plus 4. So the dm by dx is going to be plus 4. And your graph is going to be some kind of a curve with reduced slope. Okay, like this. And next, you move past point C for plus 4 to minus 6. That means the slope here change from plus 4 to minus 6. So the dm by dx is going to be minus 6. And it's going to be minus 6 all the way down to here. Okay, you just put this one and then you get this slope. Put this one more. Okay, that is going to be the moment diagram of our beam. That's not hard, right? Okay, let's do record it. And then we go to the second step. For the second step, we're gonna draw the conjugate beam. So to draw the conjugate beam and elastic wedge, which is m over ei. Okay, and you can draw that, right? To do this, all the moment, they are positive. So our conjugate beam, if you like, let me move a little bit. So that is the real beam. And since the real beam has the external roller, what we have is our conjugate beam also have external pin and external roller. Okay, to respond to that. Okay, we have this. Our conjugate beam, and this pin still pin, and this is going to be A palm. This roller is going to be roller, and it's going to be B palm. And this point C is going to be C palm. And then you have what? 18. This 18 must be divided by EI. Okay, must be divided EI. So we can do that by divide 18 by EI. Let me put this one in 18 millimeter because I am spare the space for that. Okay, that is 18 millimeter. So this is gonna be 18 over EI, and then the graph gonna put something like this. This is because of uniformly distributed load. So this is the curve, and we will need to determine its area and its centroid. It will be somewhere here. Okay, anyway, it's going to put up like this. Like this. Okay, that is going to be all the elastic weight. They are usually, I should make a notice that point for the positive moment, they're going to point out. For the negative moment, they also point down. Okay, it's always point out of the beam, point up or point down. Okay, and the last one, we just put this one. This is going to be triangle. This is going to be easy. Our life going to be really happy with this. Okay, this is our conjugate beam, and due to the limited of the area, okay, we will draw the free body diagram on the conjugate beam. Okay, conjugate beam. Okay, we have really limited area. So what we have is gonna be pin, right? Let me move, and the next step we will move to analyze the conjugate beam. That means we should only take this portion of the lecture up. Okay, we only consider conjugate beam now. The third, analyze the conjugate beam. When you analyze the conjugate beam, you gonna determine the reaction, the shear, and the moment. And then we also have the concept of this. The theorem number one, the theta or the slope of the real beam is going to be V prime on conjugate beam. Okay, beam. And what we have is, next we have the deflection. The deflection is going to be M prime of conjugate beam at that point. Okay, that is the start. Okay, what we have is we going to determine this is, let's say this is going to be the A sub y prime, and this is going to be B sub y prime, and our beam going to have the length as before. That is 2 meter and 3 meter, and we can determine the resultant of the triangular area easily, because it's going to be 1/2 of 3 and times 18 divided by EI. So what is going to be what? Going to be cos 2 9. 9 times 3 is 27. So this is going to be 27 divided by EI. Okay, this is for this triangular area. And it's not enough. What is the position of their acting point or the centroid of the area? So this is, you know that this is going to be 3 divided by 3. This is 1 meter. And since this is 1 meter, this is going to be 2 meter. Now, we arrive here, okay, of this one. This one is the f sub r. This also f sub r. And we don't know its area yet. Okay, and also the centroid of this one will be x bar from here. And if we like to determine the f sub r is going to be the area. It's going to be the area of this curve. It's going to be the area of this curve. You can find the area of this curve by integration of this curve. And before you can find that, you got to find the equation of this curve. Okay, you can find the equation of this curve by finding the moment equation as the point x from this one. Okay, so you may draw the equation of x in which x is going to be from 0 to 2. And then what we have is you remember, we have a sub y here. A sub y is what? A sub y is 14 kilonewton. Okay, let me put this here. 14 kilonewton. And also, if we expand this a little bit more, we have what? We have the uniform load here of 5 kilonewton. 5 kilonewton per meter. And this is going to provide you with the resultant of 5x. And then you may have the length here of x divided by 2. Okay, and then what we have is the moment here. That is m. So if you summation of the moment here equal to 0 and put this one as the positive, so m is equal to 14 times x, so it's going to be 14 times x, 14x. And what we have next, this one is going to rotate in the way of m. Since it's moved to an opposite side of this, it's going to be minus 5x, and then it's must times x over 2. So you have this m as what? As 14x minus this one is 2.5x squared. That is the equation of the m moment here. Okay, this is going to be the equation of the moment here. And over here you have is for m over ei. And then you can determine the f sub r, okay, by integrating this equation. Okay, let me move a little bit more like this. Okay, we try to determine f sub r. Let me compute beyond this area to this area. We may find, let me try to move this to make a little bit area here. Okay, we're looking for the f sub r. Okay, so what we have, f sub r is going to be equal to the what? The integration of m over ei dx from 0 to 2, only from this to this. So you're going to integrate. Okay, you take m, this one, divided by ei. Since ei is constant, take the ei out, and you do the integration from what? From 0 to 2. And the m going to be this equation, going to be 14x minus 2.5 x squared, and then dx. Okay, if you can do U is going to be what? It's going to be equal to 1 over EI, and this is going to be 14x squared divided by 2. 14x squared divided by 2. And minus, this is going to be 2.5 and 2.5 and x cubed divided by 3. Okay, and then you integrate it from 0 to 2. You arrive at the result of 21.333. This is going to be 21.333 over EI. Okay, we have this of 21.333 over EI. If you like to put it over here. Okay, next we're going to find x bar. To find x bar, that means you got to find the moment of this area. Okay, with respect to reference points here. Okay, and this one is what? This one is f sub r times x bar. So we have f sub r times x bar, and it's going to be equal to integration of the moment here, okay, with the moment arms x here. So it's going to be x and integration of m over EI and dx from here to here, from 0 to 2. That means you're going to have this equal to, since 1 over EI, take it out, and it's going to be integration of x times m. That is going to be the integration 0 to 2 of x times m. 14x minus 2.5 x squared, and then dx like this, and we have this equal to, this is going to be integration on 0 to 2 and 1 over EI, don't forget it, 1 over EI, and this is going to be 14x square and minus 2.5x cubed, okay, and then dx, and again it's going to be equal to 1 over EI, and this one, this is going to be 14x cubed divided by 3 minus 2.5x power 4 minus 4, and you integration it from 0 to 2. Okay, and you do this, you can get the value of this of 27.333 over EI, and then the x bar the x bar will be equal to divided by f sub r. F sub r is over here, f sub r divided by 21.333 over EI. Okay, you do integration of this and you will get it for 27.333 divided by EI, and then finally you arrive at the x bar of 1.2813 meter. Okay, that is nice. This is going to be equal to 1.2813 meter. Now you are ready to do the calculation for the A sub y prime and B sub y prime, and you may notice that the A sub y palm also equivalent to the shear. For example, if you cut the beam here, you get the A sub y palm here. You take the convention of the side, the V here, going to be in opposite direction of V palm here, opposite direction of A sub y palm. Okay. Then what we have, we're gonna find theta A and theta B. Next, to determine this, we got to find the reaction. We do the summation of moment, summation of, let's say, over here, M sub B palm equal to 0. So A sub y palm gonna rotate like this. So the rotation of that's gonna be positive counterclockwise. We have what? A sub y palm, which is 5 meters from here. And then this is gonna be counterclockwise. This is clockwise, this is clockwise, so it's gonna be equal to, this is 27 divided by EI, 27 divided by EI, and this take moment here. How far from here to here? That is 2 meters, so it's gonna times 2. And then this F sub R, okay, 21.333 over EI, gonna rotate in the same direction of this one, 21.333 over EI. And how far from this one to this one? You may use 5 and then minus x bar. Okay, so that is going to be 5 minus x bar 1.2813, and like this. And then you make determine this time A sub y palm. A sub y palm gonna equal to this one and this one, and then divide by 5. Stop, pause the video and try to push into your calculator. This is gonna be divided by EI. Okay, and by the elastic curve that we draw previously, the direction of this is gonna be like this, and this is gonna be what? This is gonna be theta sub A. That we like to determine. Okay, and then the next one is the what? Now we have the theta sub A already, so we have this. Okay, this is 26.667 over EI. Then summation of F sub y equal to 0. We gonna determine downward B sub y is positive, so our B sub y is downward. B sub y palm is downward. 26.66 is going to plus 26.667 divided by EI, downward. And this 2 is upward, so it's equal to 27 divided by EI. This is 27. And then divided by EI. And then we still have this one plus 21.333 divided by EI. Okay, if you do this, you will get the theta sub B equal to B sub y palm, and it's going to be 21.667 and then divided by EI. And if you see the elastic curve, this is going to have, no, not this one, it's going to have the curvature like the rotation in this direction. And if you like, you can determine the value of this directly if you like. Okay, what we have E and I, right? So this one gonna be, let's say this one gonna be 26.667, and then you have what? You have EI divided by E is what? Is 200, and then 10 power 6 kilonewton per square meter. We calculated basis on kilonewton, so this is going to be 10 power 6, and then the I, okay, the I going to be 60, and 10 minus 6 meter power 4. And this one gonna cut this one, so you can get the result easily of what that is gonna be equal to is theta sub A, and the unit is gonna be radian. Okay, theta sub A, slope at A, 2.22 10 minus 3. Okay, and also you do the same thing of this, you will get theta sub B of what? Equal to 21.667, and then divided by this is 260, 260, and you will get this equal to, the unit is going to be in radian, 1.806 10 minus 3 radian. Okay, that's you get, or you have both in equation and also in the value. You may put this into the table on the top of this. And now we have the other left. Okay, this one we have, if you like, theta sub A, and you have theta sub B, and you still have V sub C and V sub D. Okay, let me take you back over here. And you get this one for 1.806 10 minus 3 radian, and this is going to be 2.22 and 10 minus 3 radian also, and the rotation here is here. That is going to be the slope. Gonna measure this, and the slope is going to be here. Okay, you have this to here, and you may have this to here. And next, we still have V sub C and V max. Let me work on the V max first, if you like. Okay. The V max is going to occur, the max going to occur here. Since V max occur here, we don't know the position that V max occur yet. So we got to determine the distance of V max by the condition of the slope is 0 or equal to V palm equal to 0. So we need to cut the beam like this. So we just cut it along the way down here. And when we cut it, let me move it a little bit. Okay, it's going to project to the conjugate beam, and you may see we arrive here with this one with the cut. Okay, after we cut, the beam is going to be less than 3 meters. Okay, and B sub Y palm is here. We have it for 21.667 divided by EI. And we have this is going to be about 1.5 centimeter. This is going to be about this. What the value of this, which is equal to this? Okay, by similar triangle, we have this is going to be, let's say this y. We have y over what? Over this 10 that I measure here is going to be x, y divided by x equal to, this is 18 divided by EI, and the distance here is 3, so this is going to be 3 here, and it's going to be what? Cut 6 over EI, and then we will have the y equal to 6 over EI times x. So this is going to be the y here. Okay, and what we have is going to have the uniformly distributed elastic weight. And for the cut here, we have what? This is the x. And we have this one for the M palm. And this is M palm going to be our Vmax. Okay, our M palm is going to be our Vmax. And it's occur when the V palm, which is the slope, is equal to 0. So what is going to be this one? We're going to do the theta first. Okay, so over here we find Vmax. Okay, when we find Vmax, we got to find the distance x first, and we do the summation of what? Summation of the f sub y equal to 0 by doing this. And now we have this one. Now what is positive? So our V palm is downward. It's gonna plus 21.667 divided by EI, and downward, and then we're going to have this one. It's going to be here. It's going to be 1/2 times x times 6x over here over EI, and then you may have this for what? This is 3x squared over EI. So this one is 3x squared over EI, be equal to 3x squared over EI. Okay, and this gonna be 0, and then this one cuts. Now we can determine x. X is equal to 21.667, and then it's gonna divide it by 3, and since it's x squared, so it's gonna have square root here. And if you put everything together, you will get the x equal to 2.68 2.687 meter. So this is going to be 2.687 meter, which is less than 3 meter. Okay, so my assumption is correct. Okay, now you're going to determine Vmax. That means this one, summation of moment equal to 0. This one positive. So you have this one for M palm like this. And 21.116 is going to be the same direction. So you take moment here. Okay, this one is up. So it's going to plus 21.667 divided by EI. And then this one going to time this X, 2.687. And this one going to rotate in opposite direction. So equal to 3 divided by EI. And then it's going to be what? It's going to time 2.687. 2.687. 2.687 square. And then we have the distance here. That is going to be x divided by 3. So we're going to time this one for 2.687 and then divide it by 3. Okay, and this 3 cut this 3. So you got 2.687 power 3 divided by EI. And after you do the calculation, you will get M palm.ซึ่ง sorry, it's going to be Vmax. Okay, M palm Vmax is going to be equal to minus 38.82 divided by EI. Minus is mean downward. Okay, minus is mean downward. And then if you like, you may put this one. It's going to be what? It's going to be 38.82 and then divided by EI. Okay, divided by 200 and 60. You can reduce the form of this, you know this, right? And then you have this one equal to Vmax equal to 3.23 millimeter. So 3.23 millimeter, and then it's downward. And you can put this one on the top. Okay, and then we have the Vmax already. And the author, we're gonna find V sub C. To find V sub C, that means we're going to draw another free body diagram, but this time we're gonna draw it cat C palm. Okay, our free body diagram gonna be something like this, and this is here 18. This is 18 divided by EI. Okay, and then it's going to be all the way down here for 3 meters. And you have this one for 27 divided by EI. This is the resultant force of this, 27 divided by EI. And this one, the same. So this is B palm, 21.667 divided by EI. And we have this for 3 meters. Okay, it's different. And this one gonna be C palm. And what we have is gonna be the moment m sub c palm, which is going to be v sub c. And also if you like, okay, you may have this is going to be v sub c palm, which is going to be zeta sub c. It's up to, if you like to determine, you can determine everything. Okay, so by the way, we have is summation of m sub c palm equal to 0. Take the moment here, so this one gone, and then we have what, m sub c palm here, so the rotation here is positive. We have m sub c palm, and this one is the same rotation, plus 21.667 divided by EI, and it's gonna time 3. It's gonna time 3 meter. And then this one in opposite direction equal to 27 EI time this one. This is going to be, as you know that this is 1 meter, so time 1. And if you put everything in your calculator, you will get v sub c equal to, okay, this is going to be m sub c palm equal to, okay, go to what, 38. If you pause your video clips, put them into the calculator, and it's going to be negative, okay, or it's going to be 38 divided by EI downward. If you like to put it in the equation, so this is going to be 38 and divided by, before this we have this one, as before this one, 200. Okay, if you can reduce this one, and then you get this for 3.1, this is going to be 3.16 millimeter, and it's going to be that one. So it's very close, okay, 3.23 and 3.16. Now, you can put this one back here. The slope at C, you got it for 3.16 millimeter downward. Maximum you get is 3.23 millimeter downward. Okay, and now let's check. Let's check. We got this one, okay, to this one. If you put this one as the 3.23, it's going to be hard to do so. That is 6.46. Let me put it to scale 3 min times 2. Okay, and this is going to be very close. This one and this one will be very close. And the scale is hard to determine because it's supposed to be closer than this. The area, if you put, it's going to be really the same curve. Okay, and you can see the exact elastic curve after you determine the value of the slope and of the deflection. And now you may check if this beam is strong enough when you compare with the allowable deflection. Okay, that is what we have for this special problem, in which this time I introduce you with the uniformly distributed load, and then you do the same calculation procedure, except that the uniformly distributed load gonna produce you the curve moment, and then you're going to have the curve elastic weight, and then what extra from here is just determine the f sub r by integration and x bar by integration. And I know you can do it because we have this in mathematics before. Okay, we study theory of structure. That's going to be a little bit beyond what we have it before. Okay, have a nice day. That is all I have for this clip. Okay, bye bye.